Hello, everyone. Today's video is about subspaces. The idea behind the definition of a subspace is that a subspace is a subset of our space Rn that satisfies some important properties. Before going to the definition of subspaces, I'll give you 4 examples of possible subsets of Rn, which we will use to determine which are subspaces and which are not. So these, for now, are just subsets of Rn. The first one is a subset containing just 2 vectors inside R3. It's a subset with 2 elements, the vectors 1, 2, 3, and 0, 1, 2 inside R3. Another kind of subset that we will consider is the span of a set of vectors. In particular here, I'm taking the span of the set S containing the vectors u and v. This span is the set of all linear combinations of vectors u and v. It is also a subset of R3. Another example is the set S1, which contains all of the vectors in R3, v1, v2, v3, such that their entries satisfy this particular property, i.e. that v3 is equal to 2v1 plus v2. So it's a relation between the entry of the vectors. The last example that we'll consider today is this set of points in R2, x and y, such that x squared is equal to y inside R2. Okay, we'll now determine whether these are subspaces or not, but before doing that, I need to tell you what a subspace is. And a subspace is characterized by having 3 properties. We say that a subset of Rn is a subspace of Rn if these 3 following conditions are satisfied. First of all, the 0 vector must belong to our subset. So 0 must belong to W. Then W, to be a subspace, must be closed under sums, which means that whenever I have 2 elements U and V inside W, then I need to check that also U plus V belongs to W. And W is closed under scalar multiplication, which means that whenever I have an object of W, U, and any scalar C, a real number, then I need to check that also C times the vector U belongs to W. If W satisfies these 3 properties, then we say that W is a subspace of Rn. Let's go back to our example. The first that I want to consider is the set S1, which is the set of vectors whose entries satisfy a certain linear relation. V3 is equal to 2v1 plus v2. Is S1 a subspace? Well, we can check the definition. The first thing that we need to check is whether the 0 vector belongs to S1. So the 0 vector has entries v1, v2, and v3 equal to 0. Let's check that this relation v3 equals 2v1 plus v2 is satisfied for the 0 vector. v3 is 0 is equal to 2, 0 plus 0. This is true. We just wrote 0 equals 0. In other words, 0 is a vector in S1. Let's check the second condition. Suppose that we have 2 vectors here, u and v, and I'll write them expanding out their entries. So we'll have u1, u2, and u3, and v equals v1, v2, and v3. The question is, does their sum belong to the space S1? Well, let's see. We know that since u belongs to S1, we must have the relation u3 is equal to 2u1 plus u2. And since v belongs to S1, it must satisfy the relation v3 equals 2v1 plus v2. Now, let's wonder about u plus v. This vector has entries u1 plus v1, u2 plus v2, u3 plus v3. And what we want to understand is whether U1 plus V1, whether this relation is satisfied, which is U3 plus V3. We wonder whether this is equal to twice U1 plus V1 plus U2 plus V2. But this is true because if you use these two relations that we wrote down up here, then U3 plus V3 is nothing but 2U1 plus U2 plus 2V1 plus V2, using these two equalities for U3 and V3. But then that is exactly what we want it to be equal to. By doing a partial factoring of the factor 2, we get 2 times U1 V1 plus U2. So indeed, the sum U plus V also belongs to S1. There is one last check to do, which is, suppose now that the vector U belongs to S1 and C is any scalar. Since U belongs to S1, that's the same as saying that U3 is equal to 2U1 plus U2. But now we should check entries of the vector C times U. And this is entries CU1, CU2, CU3. Now the question that we want to answer is whether C times U3 is equal to C 2CU1 plus CU2. And this is true because this equality is the same as the relation that we have up here. Factoring out a C, we get that this is CU3 equals C times 2U1 plus U2, which is true because U3 is equal to U1 plus U2. The conclusion is that S1 is indeed a subspace. Let me write it here. S1 is a subspace of R3. Let's have a look at another example. Here's our set S containing two vectors U and V. Well, S is not a subspace because, for example, the vector 0 does not belong to S, since S only contains U and V, and 0 is different from U, and 0 is not V. So it's not a vector in there. The answer here is no. S is not a subspace. Let's have a look at this other set, S2. The set of pairs xy such that x squared is equal to y in R2. And let's perform our checks. Does the vector 0, 0 belong to S2? The answer is yes, because 0 squared is equal to 0. Now, the second check is whether this is closed under sums. So let's take two vectors, x1, y1, and x2, y2 inside S2, which is equivalent to saying that x1 squared is y1 and x2 squared is y2. Now let's add them together. If I add these two vectors, I get x1 plus x2, y1 plus y2. But now if I take x1 plus x2 squared, this is equal to x1 squared plus x2 squared plus twice x1, x2, which is equal to y1 plus y2, which is what we would want. But there's this extra piece, 2x1, x2, which is different from y1 plus y2. In other words, this set S2 is not closed under sum. And therefore it's not a subspace. We come to the last example, and I let it be the last because it's the most important one. Given any two vectors in R3, u and v, is their span a subspace? The answer is yes, and we will check it by checking all of the three conditions. And it will turn out that this is not only the most important example, but also the only example. Let's not get ahead of ourselves. Let's just check that the span is equal to, is indeed a subspace. Well, the first question is, does 0 belong to the span of UV? And the answer is yes, because I can always write 0 as a linear combination with 0 weights of U and V, 0 coefficients of U and V. So it's always in there. Now let's take W1 and W2, two elements of the span of UV. So I'll write W1 as A1 U plus B1 V. Or maybe I'll use A and B, and then I'll write W2 equals CU plus dV for some other scalars. Now, if I look at the sum, W1 plus W2, this becomes AU plus BV plus CU plus dV. But if I factor out the vectors U and V, I get A plus C, U plus B plus D, V. And this is very much a linear combination of U and V. So this does belong to the span of U, V. The second condition is satisfied. Let's check the third. For the third condition, I need to pick a vector inside the span of U and V, so a linear combination of U and V, and a scalar C. Now, if I look at CW, this is nothing but CAU plus CBV. And it is indeed a linear combination of U and V with coefficients CA and CB. So this does belong to the span of UV. The conclusion is that the span of UV is a subspace of Rn. In fact, I want to recollect that in the following theorem, which says exactly what we just proved in that example. If I take the span of any finite non-empty set of Rn, then that span is a subspace of Rn. In other words, I guess the words that you want to remember here is that spans are subspaces. The span of any set of vectors is a subspace. In particular, there's two important but also kind of obvious examples of subspaces, which are Rn itself and the set only containing the zero vector. In fact, we saw that Rn can be written as the span of the standard vectors, E1, E2, all the way to En. So since Rn is the span of a set of vectors, Rn is a subspace of itself. By the theorem. And similarly for 0, we can write 0 as the span of the set only containing the 0 vector. So again, by the theorem, the set containing just the 0 vector is a subspace. In the next video, we'll see some important example of subspaces that come from the theory of matrices that we've been developing. To a matrix, we will attach a series of subspaces. I'll see you in the next video.